Hello students, so in this lecture we shall take up magnetism. First one we will start with paramagnetic relaxation. Now we can visualize it in the case of an oscillating magnetic field. When the magnetic field is zero, the magnetic dipoles oriented at random, and so there is cancellation and there is no magnetization. Now when a field is applied, that means an oscillating magnetic field, there are certain periods which elapse before the magnetization has reached equilibrium. Some time will be taken before it reaches equilibrium, and the time taken for the build-up of the magnetization is called the relaxation time, given as tau, and it is also expressed as the rate of change of magnetization is equal to saturation magnetization minus the current magnetization divided by the relaxation time. The magnetic field varies sinusoidally. However, due to this lag, the magnetization per unit volume will be generally lag behind in phase. So this is the lags behind the phase. So if this is cos omega t, where the magnetization is cos omega t minus phi, this is what is known as a paramagnetic relaxation. Now coming to magnetism observed at surfaces and thin films, the magnetic long-range order in the absence of anisotropy, it is impossible for Heisenberg's spin system in 2D and 3D. This long-range order is not possible in 2D and 3D. However, it is possible in 3D systems. Now, in an ordered lattice of magnetic spins, which can have any orientation, the excitations are called spin waves at low temperature. Now, in these waves, the spin on neighboring lattice sides, they twist with respect to each other, giving rise to magnetic energy omega k, which is again proportional to k square. And these quantized excitations that we talked about in spin waves, they are called magnons. Now, we can actually find out the number of magnons as they follow B statistics. So this is the equation of finding out the number of magnetons, Gk into Nk plus k, where Gk is the density of states, and we ultimately come out that, so this is Kb H by k square, so this is the equation, and we get omega is equal to ak square. So using these relationships, we ultimately get the value of number of magnons to be proportional to natural log of k, and was proposed by Merlin and Wagner. So there it is. Now theoretically we cannot have long range order in 3D, because long range wavelength, that means a low wave number, excitations are possible in these systems with negligible energy. That is why we cannot have. But once a monolayer or a magnetic system on a substrate, we can have broken symmetry. So although it is not possible in a two-dimensional system, but if we get in the same of a film, we can have a broken symmetry. Now coming to the anisotropic interactions in 2D and 3D magnets. In 3D magnets, the basic magnetic interaction is exchange interaction, and related to spin on lattice, that is is equal to summation JSI and SJ to adjacent interactions through summation of adjacent lengths. Now Heisenberg's Hamiltonian between spin Si and Sj, this is Heisenberg's Hamiltonian J, and this is the exchange coupling constant. So when an external magnetic field is applied, there is symmetry breaking occurs. So due to that, we have a value of an energy which is given as mi into h, where the combination of these two systems is plus minus half. So according to the Ising model, the magnetization is between T minus Tc to the power 8, where Tc is the Curie temperature and it is T is greater than Tc for the paramagnetic material. Magnetocrystalline anisotropy, when you have an energy K, due to the anisotropic changes distribution in the crystal field, which orients the magnetic moments along the specific crystallite direction. This form of this energy depends on the crystal symmetry, the most often encountered being the uniaxial symmetry, where you have a C-axis, which is called the easy axis of magnetism. Now, in a cubic crystal such as a VCC, like in the case of iron, we can have a cubic anisotropy which is expressed in terms of directional cosines. So we have three directional cosines, alpha 1, alpha 2, and alpha 3 for a three-cube system. So we can express the energy K in this following fashion. There won't be any second-order terms as this one, as this is equal to 0. And the easy axis for iron is along the 1, 0, 0, 0 direction, which corresponds to K1 greater than 0 and K1 greater than minus K2 by G. For nickel, the easy axis is again 1, 1, 1, and a 4% silicon added to iron for 4 silicon gives polycrystalline Fe at 100 texture, making it easy to magnetize the plane of transformation, leading to a small energy loss when used with AC. Now there are several other anisotropic terms which can be important in particular circumstances, and these give rise to demagnetization energy, these anisotropic terms. Now this demagnetization energy again is a microscopic effect caused by the shape of the sample and derives from magnetic self-energy, that is E. Now, self-energy is the interaction of the demagnetization field inside the sample with the magnetization, or equivalently the integral of the energy density of strong field over all space. If, for example, the magnetization is perpendicular to the thin film, there is a large energy due to dipolar field outside the film. But if the magnetization energy is in the plane of the film, this effect is minimized. Now, in real films, these causes the formation of the domains. This demagnetization magnetization energy is the reason of formation of domains. Now, in uniaxial crystals such as HCP cobalt, there will still be a small field outside the film connecting the two oppositely oriented domains. In cubic crystals, even this can be avoided by the formation of small closure domains at the ends of the film. Now, the price paid for these domains is the energy of the interface between the oppositely magnetized domains, that is called the block, the Neal walls, and depending upon how the spins rotate from one domain to the another. So, if there are two domains, this is domain 1. So, this is a domain 1, and this is a domain 2. So there are spins on the both sides, so they are interconnected. So whenever we are going, how they are changing, that means from this direction again to this direction, this change, we have these walls as called the block or the Neal walls. So higher is the angle of change, the thicker will be the block or the Neal wall.